Go ahead, Max.
So I'm going to present this paper, which is named Exponential Decay of Rényi Divergence under Fokker-Planck equations. So we should write our 5 code if you want. So we are going to focus on the Fokker-Planck equation, which is the following one. So to define the Fokker-Planck equation, we need V, which is a smooth function, which is our potential, and a probability distribution P at time 0, which is supposed to be decreasing fast enough when at the infinite. And the Fokker-Planck equation is the following one. So the time derivative of a probability distribution is equal to the divergence of the probability distribution times the derivative, the gradient of the potential plus the Laplacian of the probability distribution. So we already know some results about the Fokker-Planck equation, and especially one about the relative entropy of the probability distribution. So just to make a quick recall, the probability distribution is defined with the following formula. So we have two cases. If we have two probability distribution, P and Q, and if P is absolutely continuous with respect to Q, the formula is the following one. So P over Q times the logarithm of P over Q, and we make the integration with respect to Q. Otherwise, if P is not absolutely continuous with respect to Q, we take infinite. So we know one result about the relative entropy in the Fokker-Planck equation is the fact that if we have this assumption, so the fact that the Hn of the potential is always greater or equal than K times the identity matrix, we know that the solution of the Fokker-Planck equation is going to converge toward the stationary distribution, which is the Gibbs stationary distribution, which take the following form. So it's less the exponential, it's exponential less the potential. So here we make the assumption without the loss of generality that it's normalized. And we even know the rate of convergence of the solution, which is the fact that the relative entropy of the probability distribution at times t from the probability distribution infinite is less or equal than the relative entropy at time 0 times an exponential. To a quick remark is the fact that with this assumption, we are going to know that this probability distribution is going to verify a log-Sobolev inequality. And if we use the log-Sobolev inequality, this log-Sobolev inequality and the ground wall inequality, we are going to find this theory. So the idea of the paper is that if we know that, we would like to extend it to other divergence, and the paper is going to introduce the Rényi divergence in order to find results looking like this one, but for the Rényi divergence.
But under the same assumption?
Yeah. Just to give the definition of the Rényi divergence, so if we take two probability distribution with P and Q, with P absolutely continuous with respect to Q, the Rényi divergence take the following formula. Let's take alpha, which is our order. If alpha is equal to 1, we take the same definition that the relative entropy. And if alpha is different from 1, we take 1 over alpha plus 1 times the logarithm of the integral of P over Q exponent alpha. And the goal of the paper is to find the convergence rate with respect not to the relative entropy, but to the Rényi divergence. But we know that the Rényi divergence, when alpha is equal to 1, is the relative entropy. So the paper gives its main theorem, which is the following one. So if we have the same assumption than before, so the assumption on the Hn and the assumption on the probability distribution at time 0, we have that there exist two constants, tau and c, giving this inequality. So the Rényi divergence of Pt from P infinite is less or equal than c times the Rényi divergence of P0 from P infinite times an exponential. And this time, this inequality is only valid when t is less or equal, is greater or equal than tau. And we do even know the values of C and tau, depending on alpha. So for tau, we have two cases. Either alpha is between 0 and 2, and tau is equal to 0. Otherwise, it's equal to 1 over 2k times the logarithm of alpha is 1. And for C, we have three cases. One for alpha between 0 and 1, one between 1 and 2, and one for alpha bigger than 2. What could be interesting to notice is that if we take alpha equals to 1, so this time tau is going to be equal to 0, and C is going to be, in this case, so C is going to be equal to 1. And so if we look back at the inequality, we have the same result than the results we had before. So just a generalization of the result.
Do they discuss in the paper what happens before this tau time kicks in?
Yeah, I'm just in the example right after. Okay, so I'm going to make the proof later, but the proof is mostly using the fact that, well, at the beginning we proved the inequality for alpha equals to 2, then we prove it between 0 and 2 with the help of the case alpha equals to 2, and then we prove it for alpha greater than 2. Okay, so to answer the question, the paper takes the following example. So with this potential, which is x squared divided by 2 plus 0.5 times the logarithm of 2 pi, with this initial distribution, so a normal distribution with mean 1. And so with this case, where it's possible to make the direct calculations, so to find the probability distribution at every time, and to compute the Rényi divergence at every time between Vt and b infinite.
So this additive term on B, is that just because of the normalization constant?
On the V?
Like capital V, I mean, it's a quadratic, right?
Yeah, but yeah, it should, because on the Fokker-Planck equation, it doesn't change anything. Could you change the
Yeah, exactly.
So yeah, you're right, it should be for the normalization.
It's just so that, I guess this is just like a normalizing constant.
Yeah, I think so. I didn't check
Because
that.
if you take the exponential, you have the correct.
Yeah, then you integrate up to,
Yeah.
it integrates to 1.
Yeah.
Okay, so what we see is that if we take, so if t is big enough, we are going to have only this exponential term. So we are going to have alpha divided by 2 exponential less 2. But what we also see is that if alpha is very big, so at the beginning, this term and this term are going to disappear, but this one is going to be equal to 1. So we see that it's not true when t is too small compared to alpha. And so they take this example, which, well, I mean, this is the same example, but they plot the results for different alpha. So they plot, I don't know if you can see. Yeah, plot this the Rényi divergence of order alpha at time t divided by the Rényi divergence of order alpha but at time 0. So this is less straightforward than this.
But you took logs, right? So
Yeah,
maybe it's
right.
now
Maybe
it's
not
negative
right.
2.
And we have log c. Log c. And that's only true when t is greater than 2. And so this is the case alpha equals to 10, in the other it's 1 and 0.05, and you see that you need some more time to have access to the linear plot when alpha is big. Okay, so before the paper make the proof, they want to give an intuition about the Fokker-Planck equation. It's the fact that you can convert the Fokker-Planck equation into a gradient flow equation. So the goal of this is to define a structure, a manifold, and a metric tensor, and to identify the Fokker-Planck to a gradient flow equation, which is an equation of the following type. So if x is a function, the goal is to find the time derivative of x equal to the gradient of another function e, which is a function of x. And so the goal of the paper is to show that we can transform the Fokker-Planck equation into this kind of equation, having x equal to the probability distribution and e to the Rényi divergence.
So x would be the density.
Yeah. X, we are going to have this formula. The paper doesn't give all the details about the space, it's only to give the intuition, so I'm going to do as they did, because I don't catch every detail, but so they define the manifold, which is the following one, so all the functions that are absolutely continuous with respect to p infinite, and that are smooth, and the tangent space of this is all the sine functions v on Rd having their integral equals to 0.
Wait, here we're assuming that p infinity is this e to the minus b, right?
Yeah.
And what do you mean by smoothness here?
Sorry?
Because you're saying p is absolutely continuous with respect to p infinity,
Yeah.
and then you say is a smooth. So what is a smooth? P?
P.
And in which sense? Like
guess,
C1? Or
I guess it's like smoothness, like beta smoothness, I guess.
but that would be for the exponent.
For P.
Wait, that's what I'm confused, right? So p is a density.
Yeah.
You can say it's a smooth, but I'm thinking of this should be like in the limit, for instance, it would be e to the minus v, right? So p itself, I mean, might be smooth, but it's more.
Might be because that what I don't catch is that they don't use the space to, I mean, in the proof, you don't really use it.
Okay.
But I guess it's to define, because they define a structure with the scalar product, a metric tensor and everything, and I guess they need it.
I might need some
Yeah.
technicalities
Yeah.
there.
I think so. Okay, maybe
P is smooth as a function
Of x.
of x.
Of x.
Of x as a density.
Yeah.
That's
I think so.
Yeah, but I guess as far as we're discussing here, I don't think it's a quantifiable smoothness. It's just like C1 or something.
Yeah.
Or C2, maybe sufficient regularity.
It's a notation.
Okay.
Because for Fokker-Planck, you need which regularity in this case?
You mean for the V?
Yeah.
I guess what we're discussing here is like V is convex and strongly convex. And I guess it's also smooth, but we'll have to see the proof.
There you have
Okay, so you have strong convexity already.
Yeah. Okay, so on this space, they define, so for every vector v, they define a function psi v with this, which is a function defined up to a constant, which is defined by the following equation. So v, the divergence of p with p, writing p, but it's p at time t, just to make it simpler, equal to p times the gradient of psi v equals to 0. They're also defining a scalar product, so it's equal to sum of integral made with respect to mu multiplied by alpha, and mu is defined here, so it's p divided over p infinite exponent alpha times p infinite normalized.
So I'm a bit confused here. So what is mu to start?
Mu, it's here.
That's mu, but mu?
And mu,
Yeah.
it's like for every vector mu in Rd, so I'm defining psi mu.
Through that equation.
Yeah.
Which, okay, and psi?
Psi.
Is psi of V?
No, this is the definition of psi. Mu, it's for every nu.
Yeah, so my question is, what is nu? Nu is a probability distribution? Or is
No,
it
it's
a vector, you said?
I guess, I think it's a vector.
That is a differential equation that you
Yeah, you're right.
assume that it
Yeah.
is that it has a solution. Something like that.
Maybe,
Yeah, that's weird.
maybe that just. I think so, no? Isn't it? Because you take the divergence. Divergence is in R.
No, I mean, you can say this is a differential equation for psi, that I agree, like,
Yeah.
that's okay.
Yeah.
But still, I'm not, it's not clear to me what is nu then.
But nu is a number.
It's a vector. It's a fixed vector.
It's a vector.
So you're looking.
You are evaluating the metric tensor on nu, so it must be something on the tangent space, and the tangent space I don't know what it is.
Okay. So for every vector, say in the tangent space, you have this equation for.
Yeah.
Okay.
Okay, so the scalar product, the probability distribution, and so they define the metric tensor, which is the scalar product between for nu1 and nu2. It's a scalar product between the gradient of the two function psi defined at the beginning.
Okay.
Okay. And so the main goal will be to find this equation, which is going to be the gradient for diameter.
I guess this psi function is evaluated on nu1 and nu2. Is nu1 and nu2 the input of psi?
Psi?
Because you're saying here, maybe I'm not completely wrong. Like when I'm looking at this, right?
Yeah.
Well, is psi is this the input to this function psi or?
Is it the I guess this is a vector.
Because these are okay. We were saying that these are two guys that live in the tangent space. Okay, and you're defining this metric tensor, and you're defining somehow taking this inner product, right? That's fine.
Yeah. But what I was understanding, because you're taking the gradient, then it should be an RD.
I see. Wait, these are two functions we're saying, and the inner product is just the integration of those.
Yeah.
Okay. I guess.
Yeah, it's a bit.
It's a bit confusing.
Yeah, but at the end, with all this definition of the spaces in the metric tensor, define the equation.
Yeah, I see. Okay.
Okay.
But wait, the gradient flow. It's now you're saying. I just want a differential equation that follows the negative gradient with respect to the Rényi divergence in this manifold.
They want to find this equation in this manifold.
Okay.
All right. Okay. I'm going to write the proof on the board. So they take the metric tensor of the gradients, the Rényi divergence, nu. And so this is by definition equal to the derivative of the Rényi divergence. Okay. And can we see? Yeah. Okay. So we know the formula of the Rényi divergence, so we are able to make the computation of the derivative. So this is the logarithm of an integral, so we have the derivative of the integral over the integral. Okay, this is new. Okay, then we transform nu using the first formula we had. Plus 1. Okay, then we use the divergence theorem so that we can transform this integral. We delete the divergence and we take the gradient of this. and so we are going to be able to find the scalar product between nu and another function. No, the scalar product between the gradient of psi nu and a good function that we're going to define. So I'm going to just write it in a simple way. Okay, so here we find the gradient of psi mu. With this and this, we find the probability distribution mu, and this is equal to the gradient of the logarithm of p over p infinite. So this is equal to this gradient of gradient phi here, so with phi being set to the logarithm of p over p infinite. Okay. So this is maybe the tricky point. Is the fact that this is also equal to the gradient
of grad.
C grad Rényi divergence and grad psi mu. So what we do have is that if instead of a random nu we take the gradient here, the function psi we're going to find is this function phi. Okay.
Yeah. I mean, you I guess effectively you have found a representer of this gradient.
Yeah.
Right?
I don't know where I can write because you
maybe in that corner.
yeah, maybe I can do it. It's a good idea.
Yeah.
Okay. So what we find is that the gradient of the Rényi divergence, I think we can see.
Yes, it's visible.
Is equal to less the divergence of p p times the gradient of phi. And if we make the calculation using because we know the formula of phi, and if we make the calculation with the Fokker-Planck equation, we are going to find. So if we make the calculation, we are going to find that this is equal to this. So the divergence of p times the gradient of the divergence plus the Laplacian of the probability distribution. And so this is equal, so I guess it's a plus here, this is equal to less the time derivative of the probability distribution with the Fokker-Planck equation.
Wait, and the second equality, how did you?
This one?
Yeah.
Because you know the formula of phi, which is this one.
Ah, yeah. Okay.
And the potential comes from the infinite.
Right.
So so this is the main idea to find the gradient flow equation in this space.
It's magic.
Yeah, kind of. I mean, this isn't because the paper explained that this is inspired from another paper, and that they were already doing the same kind of trick, and that all the details are in the other paper.
But maybe that one is for scale divergence, or
Yeah.
okay. Yeah.
I think so. In this one is for generalization.
Right.
For the Rényi divergence. Okay.
I mean, those results aren't those the very famous is Jordan, Kinderlater, and Otto thing, like they.
I can't really remember the name, but maybe. Okay. So now that I proved this, I'm going to prove the theorem we just discussed before with the inequality. So the idea will be to prove it firstly for alpha equal to 2. So for alpha equal to 2, I'm just going to admit a little lemma, which is mostly calculation. So the idea firstly is to define the relative Fisher information. So with two probability distribution, this is equal to the integral of the norm squared of the gradient of the logarithm of P over Q. So this is the Fisher information, and we can also define the alpha Fisher information with the following calculation. So this is 1 over alpha times the Fisher information, not of P and P infinite, but of mu alpha P and P infinite, with mu being the probability distribution we just defined before.
With mu?
Can you remind us?
This one.
Yeah. So it's, I mean, it's the integrand that you would use for the Rényi divergence, right? You're exponentiating the ratio to alpha, and then you're taking the density P infinity to integrate.
Okay. And so the lemma I'm admitting is the fact that if we suppose that the Rényi divergence of order 2 is defined, we have that the relative Fisher information of order alpha is bounded, lower bounded with the following inequality.
That's for any alpha or just alpha equals 2?
Just alpha equals 2. And this is most equal calculation, so to make it simpler than present. Okay. So, and having this, we're going to be able to prove that we have more inequality from the beginning for alpha equals to 2. Okay. Can I erase this?
Sure. Is it visible?
I don't know.
Yeah, I think that's fine.
Okay, so firstly, I need to define big phi at time t, which is less the logarithm of the probability distribution mu defined with alpha and bt, divided by infinite. And so we do know the formula of mu, so we are able to make the calculation, which is given by the following formula. So we have this with the normalization of mu, and so we do recognize the little function phi, which is
Can you leave the
yeah, sure.
for the
Sure.
just
Okay, the first one comes from what is above, and this one comes from what is under the equation. Okay, and so this is equal to alpha phi t, which is just to remember the logarithm of p over p infinite.
Yes. Alpha.
Okay, so this is the first result we need to keep. The other one is if we take the time derivative of the Rényi divergence, we have this formula. So this is just the derivative.
So I'm using these places where you have P should be PT, like
Yeah,
in the
sorry.
denominator,
Yeah.
and also there. Okay.
PT everywhere. So we are just going to use the fact that we know another formula for the time derivative of p. So Okay, and so
And is there a change of sign as well?
yeah, thanks. Okay, and if we use, so I just erased it, but if we recognize that it's exactly the same calculation we had before, but instead of having psi v, psi nu, sorry, it's equal to the same result, but using phi instead of psi v nu. So this is equal to this. I mean, I erased it, but if you replace, I mean, it's the same thing that I erased.
Yeah, but remind me, phi? What?
Because this can be replaced by divergence of p times the gradient of phi. And I had the same equation, but instead of this, I had psi nu. I think I shouldn't have erased it. But so this is exactly the same.
I see. No, but wait. I just remind us what is a small phi here?
Phi
Log
small
pt.
logarithm of p over pt over infinity.
Okay.
Right.
Got it.
Okay, so this is the gradient of yeah. So this is also, if we use the definition of the scalar product, this is equal to less the gradient, less this formula, so I take over with respect to the mu. Okay. And if we use the gradient, the fact that we know, so we are computing this gradient, but we can link it to this gradient, just taking the gradient of the whole formula. This is going to be equal to this. Okay.
Wait. So you?
I took
mean, you were working with small phi.
Yeah, and this is big phi. I'm just taking this more.
Yeah, but that's because the gradient is unaffected. That's what you're saying.
I'm taking the gradient of this,
Right.
which is equal to alpha the gradient of this, and this is equal to 0 when I'm taking the gradient.
This is equal
To zero. Because it's a constant, it's not depending on the position.
Of course. That's what you meant on. Yeah.
The position, x doesn't depend on x.
Yeah. These are density functions, and the other thing is already.
And this is an integral.
This is already an integral.
Yeah, so it doesn't depend on anything.
Okay.
Yeah,
Okay.
you're taking the displacement.
Okay, so here I'm recognizing the Fisher information
Hmm.
that we just had. So this time I need the next slide. And so this time I can use my bound. So this is less or equal than 2k times 1 less exponential 2. Okay. So I'm going to need, or maybe I can write over there.
Yeah, no, just a question because you have a negative sign.
Yeah, so I'm changing the sense. I don't know how to say it in English.
You still have a 1 minus e, so it shouldn't be negative.
You're right.
Yeah. Okay. No, but that sounds good. Okay. So,
Okay.
yeah, maybe you
Maybe I can
continue
write over
your
there,
one.
so I keep what I wrote. So I'm dividing on both sides by what's between the parentheses, so that I can make an integration. So if I'm dividing on both sides, on the left, I will be able to recognize the fact, to recognize this, the derivative of the logarithm of this formula. Okay.
You're dividing.
Yeah, I'm dividing and I'm recognizing the integral. Okay, does it seem right to you?
I agree, but I guess alpha needs to be equal to
2. I can hear that.
Okay, yeah. Yeah. Fair enough.
Okay.
In that case,
Because I mean, if you just take temporal derivative, you get the denominator and then
1 over, you have the other side, and then
Okay. I integrate, and I'm trying to have only this on the left, so I'm taking the exponential.
Yeah. Mike has a point.
Yeah.
Right. So if you just use the chain rule, you get this 1 minus e to the minus divergence q.
Yeah.
Then you take derivatives over the exponential, you get a negative d. That's exactly what it is there.
Yeah, but I'm multiplying. Okay, maybe we can make the calculation, but I'm multiplying.
No, I think
up and
you're
above.
fine. You're fine.
Yeah.
You're fine. Yeah. Okay.
Because I'm multiplying and dividing by the exponential positive.
Yeah.
So it's going to give the same thing. So if we make the integration, we are able to reach this formula. So I'm doing the integration. I have 2 logarithms on the left, so I'm taking 1 on the right, I'm taking the exponential to have only this, and this is going to give the formula. Okay. And what I know is that logarithm, the 1 plus x is less or equal than x. So I'm having this, and we are almost there. Because I have almost the formula we had at the beginning. I'm just multiplying and dividing by the Rényi divergence at the initial distribution, so that I can exactly fit the formula. And this is equal to C.
Yeah.
Okay.
Let's take this away.
Okay. We find exactly what we wanted to find, which is this, with C being this constant, which is what we wanted,
And true for all t.
all t, so tau equals to 0. Okay. So now let's prove it for alpha between 0 and 2. Yeah. So this time we need this lemma, which is the fact that for P and Q being 2 probability distribution, the Rényi divergence is non-decreasing with respect to alpha. Okay. So I need to write again. So.
This Fisher inequality is well known.
Which one? The following, the previous one? This one? The inequality? I don't know, they prove it in the paper, but it's like a lot of calculations, so I didn't want it to do it. But
I think also